Hi, my name is Julia Silgi and I'm a data scientist and software engineer at RStudio. And today in this screencast, we're going to use this week's Tidy Tuesday dataset on voting in the UN. And we're going to use tidy models for dimensionality reduction. A lot of times when we talk about tidy models, we talk about how to use it for supervised machine learning, but we can use it for unsupervised machine learning too. And so that's what we're going to focus on in this screencast, looking at how we can use the patterns of voting in the UN to see which countries are similar to each other. Let's get started. Okay, let's explore this data on voting in the United Nations. So I'm going to read in two of the three data sets that I'm going to use that are available that I'm going to use here. So this data set from this week's Tidy Tuesday UN votes has 4 columns here. So this is for the roll call ID, so what vote it is. This is the country code, and then how that country voted there. And this issues data frame has for each roll call ID what issue it is about. So these are the two that we're going to work with here. And in this screencast, this tidy model screencast, we're going to show how you can use tidy models approaches for unsupervised machine learning. Most of the screencasts that I have done have been focused on supervised machine learning, where we take some column and then you treat that as the outcome and then predict it using the other variables. But instead here, what we're going to do is we're going to treat this data as unlabeled data and then use an unsupervised machine learning model to, in this case, to do dimensionality reduction. So this is going to have a lot in common with a screencast I did a while back on the cocktail data set from Tidy Tuesday last year. So if you want, you could compare and contrast and see what's the same and what is different, and learn a bit about, get even more familiar with this. So in this UN votes data set, I'm going to take the country, the roll call ID, and the vote. And then I'm going to do a little bit of some munging here. I'm going to make that a factor with where the levels are no. Oh, I forget. What is it? Okay, no, abstain, and yes. Abstain and yes. And then I'm going to change vote to the underlying numeric value here. So notice now instead of yes, no, yes, it says 3, 1, 3. So we've converted it to a factor and then gotten that the underlying numeric value. Because what I want is a whole bunch of roll call IDs as the features, and then what the vote was as a numeric value there. And then these I'm going to make the column names, and they're numbers right now, so I am going to make this a little bit better for a column name. I'm going to say paste 0 RCID underscore RCID. So now it looks like this. So now these can be column names, and I'm going to pivot wider. I'm going to say the names come from RCID, the values come from vote, and it's going to be really wide. So there's 200 countries and so many votes. Look at all those votes. That's a lot of votes. Notice we don't have data for some votes. Oh, and that's a tough call. We don't have data for them. So it's not a yes, it's not a no. We don't have a record for how that country voted on that. So if I was not doing a screencast right now, I might look into more like why is that data missing? But I think what I'm going to do is I'm going to fill it with a 2 like that. So that is so what is happening here is that I'm treating this like it's an abstention. So I don't, so when I do this modeling, if I had an NA, it's going to be treated like an abstention. I'm only a little bit comfortable. I'm only sort of comfortable with that decision, but I think, you know, on the fly, that's probably the best choice. It might be worth doing some more research to understand why some of these votes are missing, because it does, I mean, because like these are all here and then these are not, but it's not recorded as an abstention. I think we're just going to move on. So we're going to say that's what I'm going to do for now. And this is going to be my wide, you know, so I could do like glimpse this if I wanted, and it will tell me, you know, look at all that numeric data that I have created. All right, so it's ready. So I'm going to do two kinds of unsupervised machine learning here. The first one is our good friend, principal component analysis, and the second one is UMAP. So we need a kind of unsupervised machine learning method, which is good for numeric data, and so PC is that way. And so what we're going to do is, you know, we actually could just use recipes, because that's all we're going to use is functions from recipes. So functions for unsupervised machine learning, for you know, which you can use for for feature engineering and data preprocessing to go into a supervised model, are in recipes. But we can also just use them on their own for unsupervised machine learning. So what we do is we make a recipe. Well, we don't have an outcome, so we just make a formula that looks like that. And then we'll say data equals UN votes .df, and then it has oh gosh, that's not going to help. Let's just print it out here. It has this country, and that is not one of the oh, let me load it. Roll. Okay, so we're going to say country is not one of the predictors, not one of the variables that we're using in our dimensionality reduction. So we're going to call it new role equals, I could put anything in here. I'm going to call it ID like this. And then we're going to normalize, because PCA needs variables that are centered and scaled. So I will center all my predictors, and then I will do step PCA for all my predictors. And step PCA, the default is that we're going to find 5 components. We could change that and go up higher, you know, to like num comp 6 or 8. There's quite a number of variables here, so we could go, I don't know. I'm gonna keep it the default, but that's how you would change it if you wanted to go higher. So let's call this PCA recipe like this. So what I have done so far is I have just defined the recipe like this. So it's what it's doing when it's telling me this is I have not yet gotten it ready. I have just defined it. I have not done any execution yet. So if I want to prep it, if I want to do something, estimate something, I need to prep it. So now that's what's happening. It's going to all my data and it is prepping. And so now if I look at it, notice the differences here. There's no differences in the variables in this case. However, now it says it has actually looked at the data. It knows how many observations there are. It knows there's no missing data. It computed the mean and the standard deviation to center and scale, and it found principal components. So notice it has not done it yet up here. So that's what prep does, is it finds that from whatever training data you have put in there, which is this. Okay, so that is that part's done. So now we can start looking at the output. So we've prepped it, and then the next thing I want to do is I want to bake it. So this recipe, we defined the recipe, we prepped it, and now we're going to bake it. So if I bake it, often we will bake it with new data, like testing data or training data. But in this case, we're not doing a supervised approach. We're just dealing with this one data set. So if I say new data equals null, like this, it will give it out to me for the same training data that I used to start with. So we've got our 5 principal components here, which all are, this is the result out that we want for our 200 countries. And I can, for example, now plot this. So I can put PC1, PC2. I think I'll put some labels on there with the country. I am going to make some points. Let's make them a nice color. Let's make them sort of transparent and big, and then we're going to put the text on there. So I'm going to do it. 200 is kind of too many to put all the points. So instead of doing, sometimes I'll use text repel, geom text repel from the GG repel package. I use that a lot. But with 200, that's really too many. So I'm going to say check overlap equals true. So it will just not print some when they overlap. And then if I do like H just equals inward like this, that will work. I think that will work. All right, so that worked. So let's look at this a little bigger. So this is a principal component analysis, dimensionality reduction of the of the UN voting records in this data set for these countries. So we can see United States, so PC1, that's the direction that accounts for the most variation in these countries. So we can see United States is all the way over by itself. It is the most different from these guys over here. So Egypt, Ethiopia, Nepal, Mexico, India, Cuba, very far over here. So these are very different from the United States. And then up and down is PC2s. And so that accounts for the second most amount of variation in the components, at least of these 5 that we trained here. And so we can see, here's a Australia, Canada, Netherlands, United Kingdom kind of cluster down here. I'd be interested to know what else is in that cluster actually. Okay, so we've got all these interesting clusters of countries that are spread out in this projection of the 5-dimensional space that we created. Pretty interesting. If you ask me, I like it. It looks good. And now I'm going to just show now let's just do UMAP. So we take this whole thing. We're just going to paste it. So UMAP is in it's in an add-on package. You know what? Let's take a step back because I've shown how to use step PCA before, but there are a lot of other steps. I'm just so you know, you can do ICA, you can do kernel kernel PCA extraction. You can do these things which you actually you can say what kind of kernel you want and all these kind of things. So we have many different kinds of options for this kind of dimensionality reduction, depending on what is appropriate to your use case here. So now let's go down here to embed and move on here. So we are going to change this to UMAP recipe. UMAP prep, and it's step UMAP. And the default for UMAP is 2 components. So UMAP is based on geometry, like fancy manifold geometry, projections and whatnot. And so we could, you could go, you could increase this if you wanted, but it doesn't, I don't think it really, we want to match it per se, because it's a very, very different, algorithm than PCA, which becomes very obvious once we look at the visualization. All right, so we just have two components here. We could, of course, make that more by upping the projections that we have. And like, notice how different it is. You can really, so all we have here is two components. So we're seeing the whole space here into 2 dimensions. It's unlike principal component analysis in that situation where we had high dimensional, like 5 dimensions that we were projecting down. So this is just 2 dimensions, and we can see here, so United States is over here with these, and we have, this far away cluster of things like El Salvador, Dominican Republic, Haiti, down here, Canada, Sweden, France, Greece. So we can see what the United States is similar to and what these other clusters are like. So you can notice how dissimilar, like what a different thing UMAP is doing compared to PCA. It's just a very different algorithm. So that's these 2 kinds of dimensionality reduction that are very different, different approaches. While I'm here, you know what? Let's go back up, because we can bake, but we can also tidy. So if I'm here, let me do this. Say tidy, PCA prep, and it is the second. So if I do this, what I'm doing is I'm getting out, so this PCA is the second step, and so when I tidy it, I get out the components. If I did the first one, I'm getting the means and the standard, and then the standard deviations are down there too. But I want the principal components, and let's say I just want to look at the first 4. So I'm going to say filter component in PC, like that. So now I've just got the first 4 components, and then let me left join with these issues. Oh, so where am I? Here I am. Oh, it's called something else. It's called terms. Okay, so issues, mutate, terms. Oh, and I also need to paste. Okay, because I remember how I pasted RCID underscore RCID like that, because now they match up here. Oh, notice we've got a lot of NAs. A lot of NAs. So these are votes for which we do not have an issue. That's interesting. So now I have a choice. What I wanted to do is I wanted to tidy this and then say what issues were accounted for the most variation in countries. So for example, what issues were most important to PC1, PC2, and whatnot. But I have a lot of NAs. So I could add an issue that says, other, or I could filter them out. What I think I'm going to do here, this is a real judgment call. I think I'm going to filter them out. The other option would be to replace all those NAs with other, and then say how many of those are, how important is other compared to other things. But I think I'm just going to focus on the issues that we have records for. And then let's group by component, and let's do slice, max, let's order by absolute value of value, and take the top N, and then ungroup. So what we have now here is for PC1, whoa, it's acting crazy. For PC1, here are the top issues, or the issues associated with the top terms, which were, remember, votes, roll call votes. And are any, so that's 8. So that's right. Okay, great. So let's do that. And let's call that PCA comps. And then let's make a visualization of that. How are we going to do this? Let's put value, terms, fill equals issue. And let's do a geom call and a facet wrap with component. And we'll need to, they're all different votes on the y-axis. So let's do it like that. All right. Okay, this is pretty interesting. 1, 2, 3. Okay, so some of the votes have more than one issue, and we left join, so now there are 2 rows. So let's say position equals dodge, and this is super squashed. So let's do position equals dodge. So these are next to each other. Let's change the labels a little bit. Y equals null, fill equals null. Let's try that. All right, this is getting somewhere. So some are positive and some are negative, which, you know, of course happens with principal component analysis. Let's just value equals, well, I think, first of all, let's notice that these are in the opposite direction to these. That doesn't, I don't know, I don't get a whole lot of info from that, but okay. And then let's make sure to notice on the X that this is absolute value of contribution, like that. Zoom. All right. So I could clean this up a little more and reorder this and all, but I think we pretty much get the idea here. So principal component 1 focuses on economic development and human rights. So with, you know, there's one thing in there that's arms control, but it is mostly about economic development and human rights. So that is what accounts for the biggest variation in countries, is where they fall on the spectrum of their votes on economic development and human rights. Principal component 2 is mostly about colonialism with a little bit of, well, it's mostly about colonialism, right? And so that says that how countries vote on the issues of colonialism and a little bit of human rights accounts for the second most variation. And so remember that when we did principal component analysis, we did not know, like, these labels were not even on those votes. So it's very interesting that the way that the countries voted aligned so closely so that we were able to see this. The principal component 3 is economic development and colonialism. So we see these different combinations of voting issues and how the different countries in the United Nations are voting together. And then principal component 4 is arms control and human rights together. So this is pretty interesting, and I like a pretty interesting way to combine the voting data with the issue data. And I'm glad to be able to see this result with the unsupervised machine learning approach that we were able to take. All right, so we used two different kinds of dimensionality reduction. We used principal component analysis and we used UMAP to show how we can take all those variables about all those different roll call votes in the United Nations to be able to do dimensionality reduction and then be able to see in these new spaces which countries are similar to each other. Remember we looked at that there are many other different algorithms that are available to do this kind of dimensionality reduction in tidy models, and we can do this both for exploratory data analysis purposes or as input to a supervised machine learning model. So there's lots of options out there to use these kinds of approaches. So I hope this was helpful, and I will see you next time.